And then to start off with, we're going to have Deepak Dio, who is a fifth-year PhD student working with Dr. McIntosh. And he's going to tell us a little bit about recently quenched galaxies.
Thank you, Ben. And thank you, PHASES, for the invitation. PHASES is the group of grad students in physics and astronomy. And this semester, we are doing this for the first time, that grad students will talk about their research in popular level that even undergrads can understand. And hopefully we make you aware of what we do here. And we can, if there is any opportunity, you can collaborate with others and get to know your grad seniors. So I'm happy to see that big of a crowd. Is this audible enough?
Yeah.
Good. Okay. Yeah. And I got to know that many of are here for their first semester credit thing. So thank you for coming. I feel the pressure of this big population. Hopefully I do a good job. So let's jump in and I'll talk about dead galaxies. This is just a flashy title to attract you guys. As I go in deep, I hope I not bore you people. So yeah, I'm a PhD student in my fifth year, working on dead galaxies under the supervision of my supervisor, Professor McIntosh. He's somewhere here. Yeah, he's behind. And yeah, I'm in EMS division, SSE, UMKC. So let's begin. Murder mystery of dead galaxies, prematurely dead. So first thing, what is dead galaxy? So as we have read in the abstract, by dead, I mean not forming stars actively. And they would look like kind of this. You must have seen typical image of galaxy. If it comes in your mind, it's like a spiral galaxy, looks pretty flashy and cool. This looks like just a blob, boring blob. So they are dead, they look like that. Often they look in optical image, they look red, and that is because of the population of so many red old stars. Our sun is towards its end, it's a yellow star, and eventually when it's in its dying phase, it will become a big red star. It will look like that. So these galaxies have mostly big old red stars. They look elliptical or spheroidal. They are pretty old and massive. If you compare with our galaxy Milky Way, they are like 10 or 100 times, they could be massive than that. And they don't have the main raw fuel that is responsible for making stars, which is hydrogen gas, cold hydrogen gas. So they are devoid of all these things, and that's why we call them dead. And here we will, I have mentioned the term premature death. By that, I mean, I'm studying such galaxies which ideally they were supposed to be alive, but we are observing them to be dead. And that's a mystery for us. So I'm calling them premature death. That may be not the most accurate term, but good term to attract you guys. So let's begin with. So if you have an alive galaxy, it will look like that. Spiral galaxy, typical galaxy that you often see in popular news. And a dead galaxy looks like that, elliptical and spiral. So another term I used there in the previous one, dead and quenched, I'm using simultaneously. Quenched is pretty jargon that is used in astronomy a lot, which means quenching means something has stopped. And in case of galaxies, when it is quenching, it means star formation in them has stopped. Like no new star are being formed. And also it's a very important phase of a galaxy evolution from its initial phase of when they are making all the stars, they are alive, to their eventually death phase. They go through quenching. So it's important, since it's a very important phase of galaxy evolution, to study that and understand more about galaxy evolution. And also, why it's even more important is, again, these two plots are pretty technical plot. No need to worry about that, but I'm just showing here for reference. In layman terms, what this plot is saying that in past few billion years, the population of galaxies, elliptical galaxies, dead galaxies, has increased pretty rapidly. And that means also uh, the formation of stars, new stars, have decreased pretty significantly. And that is quenching is one of the ways through which this will happen, that no new star formation happening, and also evolution from probably from spiral to elliptical. So we have seen through observation that how important it is that quenching is playing a role in the population of dead galaxies in our current universe, which makes it important to study. So now we have to wonder, like, what causes this death of galaxies? Like, what mechanism was responsible? And we often, based on our observation in astronomy, we wonder questions like this, because as astronomer, we are also detective. We get some of the information from the universe, and then we try to put it together and make a story which is convincing to explain what we have observed. So definitely, I guess this didn't happen. It happens only in Marvel Comics. Broadly speaking, quenching, what we have understood, it happens because of these three scenarios. So as I mentioned earlier, quenching of star formation, for that, the main thing that we require raw fuel is cold hydrogen gas, which is the most abundant element in our universe. So if something happens to that gas, then something will happen to star formation too. Here, quenching of star formation can happen if cold gas is removed somehow from the galaxy, or the gas is, because of some mechanism, its temperature has changed and it has become from cold to hot, or the gas that is required to form stars, it infalls in the galaxy from some source, and then eventually that helps in the formation of star. But let's say the supply of that gas itself got cut, so it end up using what it had, but it's not getting any more. So that also quenches star formation. So broadly, we understand that these three scenarios are there. And I'm talking about this just to give you an idea about the terms that are used in my galaxy that I'm studying recently, quenched elliptical. So elliptical, quenched, all these things. Now, coming to RQEs, which I called in the abstract prematurely dead galaxies. So as the name suggests, recently quenched elliptical. Elliptical, so by shape it is elliptical. Quenched, that means it is no ongoing star formation is happening. And dead, recently quenched elliptical. So recently would mean that they have died pretty recently. So something must have happened pretty recently that they're dead, they appear dead to us. And these galaxies were first identified by Professor McIntosh in 2014. And it was a serendipitous discovery by him. He was looking for something else and ended up finding these even more interesting objects. So first, I will talk a little about what he was looking for, and then I can come to why these galaxies are special. So this is a very, for astro students, this is a very common picture that we often come across in our books or in our research, where it shows an evolution of, mostly we are focused here, that if two galaxies, they're about to merge, what are the phase they go through? So this is a paper by Hopkins in 2007. In that, he has this plot in which he is talking about when two active like star-forming galaxies, when they are merging, in the initial process, first thing happens that all the gas, star-forming gas of both the galaxies, they come together and they form like a starburst phase happens, like lots of stars forming in a very short time. And then also there is, at the center, there's a supermassive black hole, which starts getting so much food. And as it eats on the food, it becomes more active and it starts vomiting so much energy out. And that is called, in terms of astronomy, it's called AGN, active galactic nuclei. So that's one phase where you will have a very violent, massive black hole at the center doing lots of stuffs. And then a phase will come when these they are merging towards one single entity. You'll see some of the features of merging, all these tidal features. And this is the place where just after this phase, it will appear as a very spheroidal or elliptical shape, but it can appear as a blue elliptical galaxy, which is uncommon to hear, because most of the time when I'm saying elliptical galaxy, and also as I showed in the initial figure, it's red, it's a blob like a spheroidal thing. You don't see them blue. But as long as there are active blue stars alive in a phase where it is converting into an elliptical galaxy, you will see a blue elliptical galaxy. Once those blue stars are dead, which they have a pretty short span, a few 100 million years, and once they are dead, then it will look like a typical red elliptical. So Professor McIntosh was looking for that blue elliptical to also kind of like support this theory that when a major merger of two galaxies, spiral galaxies happen, there is also a possibility of getting a blue elliptical galaxy. And also in the current universe, all the merger candidates and the population that we are observing, to explain that, the number of blue elliptical galaxies, like if we have let's say 10 mergers in the current universe, then if a blue elliptical phase is there for a certain amount of time, and if you are able to catch them in the current phase, then their number will be able to explain the number of the mergers that we see. And that was the goal. And so he started looking for blue elliptical galaxies, and then end up finding blue elliptical galaxies, which is not actively star forming. Like you don't see, we don't know why we are seeing the blue color in this color plot, which is again a very astronomy related term. So if I simplify, I'll say that this is the plot in which we are comparing the brightness of the galaxy. So there are this is the brightness of star forming blue galaxy. This is the brightness of elliptical dead galaxy. And then we see here in this green shade, these recently quenched elliptical galaxies, they appear to have a similar kind of brightness as like blue elliptical galaxies. That's a very vague way of saying in terms of brightness. It's not technically very accurate, but for layman terms, that's a good way to go. And he found that spectroscopically, it's not showing any star formation. There's no signature of star formation, but they are in an interesting environment, that they are the massive central galaxy in an environment where we often expect theoretically as well as observationally them to be forming stars. So it made us wonder that why they are not forming stars when they are in an environment where they should be forming stars. And so this is the place where he stopped. He did discuss about what could be happening there that might have quenched them. Is it really a population of galaxies which came through the a galaxy which is an evolutionary phase of mergers? Or is it something different, that it was there, a red elliptical galaxy, and somehow it got gas, cold gas from some mechanism and started forming stars and started appearing blue to us in this brightness plot? That's an open question. So my job was to take these galaxies and address the first thing, like the main raw fuel for star formation, that is hydrogen gas. To ask whether they have gas or not. If they have the gas, in what form? The more I understand the raw fuel, the gas, the more I will be able to talk about the quenching of star formation in that. So there comes my part in this research. So I took the Galaxies, RQV Galaxies from Macintosh 2014 paper. And then I also took similar kind of galaxies, like which look exactly like RQVs in terms of environment, in terms of their stellar mass, in terms of morphology, the shape, they look elliptical and everything. And then I took the only difference was in terms of their star formation activity. RQVs are recently quenched, and I took the another population, which is pre-RQVs I'm calling, which are precursor to, like a phase of galaxy, which was just before they got recently quenched. That means they look more bluish. You can still see them, the active blue stars in them. And then another population of galaxies, which I'm calling post-RQVs. That is, if RQVs were dead for a few billion years, no more bluish color, no signatures of new star formation at all red star population, then you will have this. And again, this is the reason I selected this population to not only compare RQVs in terms of hydrogen gas, that are they, in terms of the hydrogen gas content, are they similar to their precursor, or are they similar to the totally evolved state, quenched galaxies? Okay, sorry. One battery went down. And while I set this battery, okay. So now that when I have these three population, I go further and I analyze their content of hydrogen gas. I do some comparative study, and I'll discuss what I found so far and what does that mean. So this is the plot, which is basically showing that one of the three properties, halo mass, is kind of also saying the big environment they are living in, these galaxies. Redshift, it is the information about how far they are from us. And stellar mass is basically how massive they are. So I selected in such a way that they are pretty much comparable to each other, like in terms of their redshift, in terms of their stellar mass, in terms of their halo mass. This was just important so that the comparative study is more reliable. And just to make an astronomy paper look good, I'm adding some images of these galaxies that I have. This one is, so the light is pretty bad for these elliptical galaxies. So this first column are the population of precursors, and the middle one is the sample population of RQVs, and the last population is of post-RQVs. Kind of they look similar, like hardly you see any feature, all spheroid. But if you do some technical analysis, plot in their brightness and all, you'll see the difference, that they appear more bluish, and they appear a bit less bluish, and they appear totally reddish. And there were some galaxies which were misclassified as RQVs by Macintosh 2014. I removed some of those, and I was able to remove those because the data he had, I had, like the image data, I had a little better data in terms of resolution. Like let's say I had 2 times much better data when you see those images. And these features, he was not able to see. For him, it all appeared like this, but I could see this feature, and then together we eliminated these because they are definitely not elliptical. So I refined the population by visual identification. And then it comes technical part. Again, I'll try to simplify things and don't bore you with the jargons of astronomy. So first thing was to check whether they have gas or not. And I go in, try to get information in the literature. As it happens to many PhD students, that you look for a certain kind of data and you don't get. So that's our misery. And what I found that I have a population of around 700 galaxies. So to make something like a significant conclusion, I would like to have at least half of the information on these galaxies. But I found that only 17 galaxies have real gas data for them. So that's pretty less, but still there is something. And then I did some, then there are about 45% of my galaxies have been observed by a certain telescope. They were trying to observe how much gas this thing has. But it was a very shallow observation, not deep. So it did observe our galaxies, but really didn't find anything in that. So I'm calling such observation as non-detections, because they observed but didn't detect gas. And then I have population of the 17 galaxies in which observation was made and they also detected the gas content. And this plot is just showing that for those 17, how much cold gas I have or they have. And also it's showing that the other 45% of the galaxies, what is the upper limit on that? Like how much, based on the some calculations that I did, based on the specification of that non-detection observations that I had, I was able to figure out that if they had gas, it would be something this much or less. So that's called upper limit. So I was able to constrain the upper limit on the gas content of 45%, and I have the actual value for 17 galaxies. And I see from this that the blue stars are showing precursors. Green one is our main candidate, RQEs, and red one is the dead ones. In astronomy, often when we plot and we are showing the galaxies, star forming and dead galaxies, it's conventional or trivial to use red color for dead, blue color for alive, and in between we choose green. So I see that for the two observations that I have on RQEs, they do show some significant amount of hydrogen gas, about between 50 to 5%. And you see all other blue ones, which are the precursors, which are actively forming stars, they do have gas. They are also in the same range. So typically also we expect galaxies with star forming to have gas, hydrogen gas, about 10% of the stellar mass. So, and the dead ones, they have pretty less, like around 1% and or less than 5%. So now this is interesting because if you have gas, at least if we talk about these two, if you have cold hydrogen gas, why are you not forming stars? What's stopping you? Then now two data points is just like very less. It's not significant. It's not giving me, helping me to find some significant conclusion. So I went and digged deeper in the literature, and I found this study by Timorania 17. In short, I'll call them T17. And they had estimated values of gas fraction for 95% of my samples. So that's good. And their estimation was based on some machine learning studies. So what I did was I compared that whether their study are worth taking for my analysis or not. So how to do that? I compared with the detection measurements, like are they in line with the detection measurements? And I also compared with the upper limit values. So ideally, I would expect their values to be less than upper limit, because upper limit gives me a max. Like max, it could be that or less. So if values by this paper are more than the upper limits, that is, if they are in this region, then definitely not trustable. But I find that all of them are, or most of them are, in this region where they are less than upper limit and kind of they are in line with the detected values. So this made me think that, okay, this T17 values are trusted and I have 95% data for 95% of my galaxies. So I'll continue using this for further analysis and I'll skip the upper limit values, because upper limits really doesn't tell me much. It doesn't constrain what area you are or what values you are dealing with. It's just an upper limit. And then I proceeded with that. And then next I looked for how to okay, if they have gas, how much, like, do we expect them to have that much gas, or do we expect less? So this study was done to figure out that, and I found that RQEs, and I did again comparison with the precursors and the post, and I found that these galaxies RQEs are in fact not gas deficient. They have enough gas. They have the gas that we expect them to have for the environment they are in. In fact, a little extra than expectation, which again makes us question, they have the gas, they have enough gas, why not forming stars? So then I'm like, okay, based on the data I have, I'm able to at least provide this information that they have gas and they are not gas deficient. What more can I talk about? So I tried to connect their star formation rate. By that, I mean that in a given year or per year, how much stars how much similar stars as our sun they are forming. And then I compared with again with the population of blue galaxies and the red. And you'll see that based on their star formation rate versus stellar mass plot, we can say that they are somewhere in the middle region, that they don't have this main sequence line is usually used for stars which are like galaxies which have which are actively making stars, and our galaxy Milky Way will lie in this main sequence thing. And below that, these galaxies, they're just below that main sequence line. That their star formation rate is good, not in terms of in comparison to active spiral galaxies, but in comparison to typical elliptical galaxies, they have relatively high star formation rate, which is weird because they are not forming stars, as we see from other spectroscopic observation. So this result is a bit puzzling. It needs more digging. Like I have to further analyze and see what more I can find from this. And then another comparison I made was like, okay, another thing is star formation efficiency. If you have gas and have high star formation rate, how is the star formation efficiency is basically like, are they forming stars efficiently? And so that comparison, this plot is pretty dense and it needs to be further revised. But in this, kind of it's showing that the galaxies which are RQEs, the triangle ones, they are in green valley or star forming region. So in terms of star efficiency also, this right value are the bigger values, here are smaller values. They are more, they have like significant efficiency as well. So we are seeing all the signatures of like they should be forming stars. Now we are questioning that, okay, we know about that they have the gas and what could be the possibility that they are not forming stars. So in the beginning that I discussed, that there are three possible scenarios. One was heating of the gas. Another was that gas supply got cut off, or the gas got removed from the galaxy. We cannot say much about that from this. We can speculate. To know further, what I will have to do is do a very resolved study from a typical radio telescope and find gas information at various points in the galaxy, and then see that how the inflow of the gas, like is it coming towards the center, is going away from the galaxy, to constrain these one of these three, at least one of these three quenching scenarios. That is the gas moving out? Did something happen that is ejecting this gas outside? Also get to study the temperature of the gas, because that would help me. Like if it is hot, then I will have to think about what mechanism made it hot. So all those things requires further data, which I don't have. So I will have to basically conclude something out of what I have, and an ideal scenario I will apply for a very resolved observation from typical radio telescope. So that's what, like, based on the results, what can we say about quenching? We couldn't say, based on the gas information that we have, I couldn't really say much about what mechanism is responsible for such a scenario where they have the gas, where star formation rate and efficiency also looks very good, are still not forming stars. I cannot constrain that. Also, I cannot constrain at the moment, are they really, as speculated by McIntosh 2014, that they are the evolved phase of a typical major merger? It's hard to say still, based on the analysis that I have, that is it an evolved phase of major merger, or something happened that it got gas from its neighbor galaxies. They are pretty isolated, but there could be still some scenarios in which they must have got some gas from their neighbors, and that helped forming stars. So that's again an open question, that what are they really? What has been their evolution so far? So yep, that's my. It's an open question for me. I'm still doing research on it, and hopefully I will be able to conclude something of what I have. And as I was making these slides, just yesterday, I found something really. I was doing some analysis to put some plots in here, and I found something really, really bad on my analysis, which I have to discuss with my supervisor, which might change things pretty badly. So we'll see. That happens to a typical PhD student in a PhD life. But yeah, thank you. And yeah, I'm open for questions if you have.
All right. Yes. Oh, I have a couple of questions, but I'm gonna sort of put a pin on it, so I'll let them talk. Okay. We have one question from one of our viewers on Zoom.
Okay.
Which is what is the role of mass and environment in the quenching of galaxies, and as we can apply it today?
So there are, like, also I have not mentioned, oftenly quenching is when it's studied in literature, there are various ways to categorize them. One is like environmental quenching, other is intrinsic quenching. So environment does play an important role. For example, if you are in big elliptical galaxy, in a galaxy cluster where you have so many galaxies around you, the whole environment there is so hot that can make the star forming cold gas hot. And also there is so many galaxies around you that when you are moving from in that big space from one galaxy to another, going towards the center, your gas can also get stripped away in the process, and that way also you lose the gas and galaxy would quench. So in environment, in a dense environment, we understand pretty well that what could cause quenching. So yeah, that's the answer. Like, environment does play pretty important role, and as I said in the example of clusters. Do you have anything else on Zoom?
Nope, that's
Okay.
it. Yes.
gas.
Yeah. Just gas. But
What stimulates the reaction of stars to form? Okay. Luckily, I think I have a slide for that question in a simple terms. Oh, not this one. Okay. It won't work? Okay. Noise. Yeah. So in simplistic way, you can see this way that you often have these star forming gas clouds together, and then they start coming together, and their gravity itself that is so dense that they'll start collapsing, and the main galaxy, like the raw material is hydrogen gas that I was talking about, but the main material to form stars is molecular hydrogen. Hydrogen will combine to form molecular hydrogen, and those small clouds will come together and they will collapse within themselves to form stars. So that's like a cartoonish way or normal way to understand. But if you go in detail, there are some necessary conditions that should happen for the star. Like for example, gas has to be cold. The number density of gas molecule in a given volume has to be huge, like 10 to the power 20 per centimeter square. All those necessary conditions has to be made for the star formation to start kicking.
something in that process that might
Yeah, like one thing is like they are coming together to form stars, and then let's say another star went supernova and ejected everything out. So that could be one possibility. Also could be another process that something happened that reheated the environment. So that condition is not met, and all those can stop. So you can have gas like how we see in case of RQEs. But if necessary conditions are not met, star formation won't happen. Which one first?
So there's like dead like could the gases like come back and we're like
That's a very good term. Yeah. So we do call these blue elliptical galaxies. I was talking about two evolutionary phase, right? That it could be, these RQVs could be one of the evolutionary phase of major mergers, like merging of two galaxies, or it could have happened that some cold gas, it might have taken some cold gas from its neighbor galaxies or somewhere, and it had started forming stars. So that taking stars.
He's still doing his presentation, so if you have to leave, I understand that. I'm not upset, but let's try to be quiet and keep conversations to a minimum, okay?
Thank you, Alice. So I'm coming to your word of using of rejuvenation. That's pretty smart because we do use that word. So one question that I was asking in terms of evolution, whether these are rejuvenated elliptical galaxies or they are really an evolved phase of major merger. So your question is like, yeah, could something happen like that? Yes. So that rejuvenation, for that to happen, it has to, let's say it didn't have gas. It has to get gas from some source. So typically in our observation, you have a limit, like you can observe until a certain brightness. That doesn't mean that, let's say I observed to a certain brightness and in this region, and I found only one galaxy. That doesn't mean that in its surrounding, there are not presence of another galaxies with, or very teeny tiny small galaxies with what we call dwarf or whatever, with gas source. If you do so one speculation, according to me, could be that if we do a very resolved study, there could be probably some small galaxies with gas, and this our galaxy might have taken some gas from there and got rejuvenated. But to confirm that, we need a resolved study. Gases, ask again. I didn't hear this earlier part. Yeah.
So one of the things that can quench a galaxy is when its gas gets heated up,
Mm-hmm.
so it's not full.
Mm-hmm.
But the a quenched galaxy come back to life if you just wait long enough for the gas.
That's a good question. And so, yeah, conditions has to be met. Like if gas is there, it got cooled. But if it didn't get dense, like it's only diffuse, then no, it will just stay there. But if somehow they started coming together and enough density, column density has been achieved, then yes. So it's possible that if the source of star formation is, fuel of star formation is provided, a quenched can come back to life.
I'll add to that, but it's a matter of time scale. So if the gas is heated by, say, the central supermassive black hole, the time scale of the gas to cool enough that it forms stars can be extremely long. So essentially, that galaxy is going to be hot for a long time, and so no reasonable amount of time will this galaxy be able to start forming stars. What's the temperature? Well, you need
20 Kelvin.
Well, that's what you need to get
Stars,
stars.
yeah.
So you need under 30 Kelvin in order to start forming stars. So basically, you don't have to heat it by a whole lot in order for you to stop the production.
Yeah. What?
Sorry? What's 30 Kelvin?
Oh. So I think 35 Fahrenheit is 273 Kelvin. So I don't know how to feel it. Yeah.
Maybe ask the professors.
I mean, you can understand in terms of number, but in terms of feeling, I think we cannot comprehend. You right? Yeah. I think so.
Okay,
Yeah.
yeah, I'll go. Your question, does this have anything to do with dark matter? Isn't that like a
Well, I don't know either, but that's an interesting thing to think about. No, I don't know.
I don't know either.
Dan, do you have anything to say on that? Like he's asking dark matter or dark energy.
Dark matter, yes, think about dark matter. Short answer, yeah. It's like this. Dark matter is all around. Like, the galaxy.
Yeah.
Dark energy is a much bigger, cosmological, really big distances.
And also it's a purely gravitational interaction, right? So these things are electromagnetic. At least we don't know at the moment it's responsible for any kind of quenching. Yep. Yes, if they are nearby and a massive galaxy come close to the little galaxy, yep, It will, just because of gravity. Mhm. Oh, yeah. Yes, we will do all galaxies. So all will also bring dwarf galaxies and everything. Can't say about that, or little small galaxies. But if you take about galaxies like our galaxies, Milky Way and massive, yes.
Most.
Yeah.
That was a great.
Yeah, that's an open question, I guess.
Question is actually just a request. One of the things that's kind of come up in a number of the contests slide as well. And I was going to ask you to clarify something that sounds like a slightly counterintuitive nuance, which is that hot gas defends star formation. And you often think about stars as being giant balls of hot gas.
Mhm.
So, connect the dots. Why do to eventually make these giant hot gas?
That's
Connect the dots.
why do we need cold? Hot air. Oh, they expand. Yes, so yeah, and that also will again come to the density, number density too. So that's why, yeah, to get the density part also, which is responsible, we need them to be cold.
Yeah, so that's kind of a tricky thing. It's counterintuitive.
Yeah.
Like the story was, oh, hot gas can't have stars. Look at the sun. Like, oh, a hot gas is unable to get the small enough concentration to eventually be able to turn into.
Yeah.
That's too big.
Mm-hmm.
So you might actually.
Yes, yeah. But we do have comparison with the theoretical studies too.
That's what I was going to ask. Theoretical studies, but also simulations.
Yeah.
Of galaxies. People do simulations that a model
Mhm.
how galaxies work. So my question is like, are some of the, you don't have to go into detail, but are some of the nuanced things that you're looking for or actually observing, are those have people actually been able to make models that demonstrate those nuanced things? Or the models kind of say part about how you replicate nuanced things that are actually observed. You kind of in the ballpark is where simulation is simulates.
So simulation does predict existence of in this merging phase, existence of blue elliptical galaxies, which yeah, in fact, this paper is a simulation paper, and we also and observationally we have seen all the different phases of merger galaxy evolution. So that's one that is like in terms of color and morphology, one information we have through simulation. But when it comes to like, there is not really much study there which specifically clears out that how do you have, can you have quenched galaxy in a environment which is like a big central galaxy in a very isolated environment where it's not really disturbed by many other things, and it has gas. How did it turn out to be quenched? That nothing like that we have as a simulation study that shows that, oh, you still can get a quenched galaxy in an environment like that. So that we don't have, yeah.
simulations are failing to generate the thing that you observe, which is a lucid simulation. Galaxies, in theory, should be generating stars. Not able. But, simulations are not.
Yes, simulation does tell that they should be forming stars. Like they are in small dark matter halo and the massive central galaxy in there. So typically, other studies have shown that that we expect them to actively form stars. So simulation has shown the other way around, and we are finding something else, like totally opposite. So that's why it's interesting.
I'll add that simulations, these like large universe in a box kind of simulations, have a really particularly hard time with handling what we call feedback, essentially the energy that's being put into the system for gas. It's not very well constrained. And so some results from simulations are less trustworthy, essentially. I think we can get one more question.
Hi, yeah, I had a. Okay. So, to me, it seems like star formation is pretty fragile with the hydrogen gas having to be so cold. And I was wondering if, like, you took into account like the differences between like from where we're seeing it here on Earth and how far away they are in the universe. Have you accounted for like the differences and like the time differences between what you're seeing and what's happening, like because like there's this thing in like time dilation where like if you look at something in the universe, you're looking at it in the past. So I was wondering, like, did you take into account like the age that you're looking at it and like what it would be now?
That's a good question and good thinking.
Okay.
Yeah, no, that's a pretty good question. And yeah, anything you're looking in the universe, we are looking at the past. But all my candidates, all these galaxies are pretty close to us, very close, near, within very nearby universe. So what you're seeing now is kind of it is there now.
Okay.
So not much has changed. But if I was looking at galaxies which are like 6 billion years ago ago is the right word? Yeah, like those, then I will have to consider all those things, that maybe I'm seeing them quench now, but probably something hasn't happened that actively right now they must be forming, they probably are forming stars. Can't tell what is happening right now. I can only talk about what is happening 6 billion years ago.
So the galaxies that are closer to us,
Mhm,
you can
yeah.
make a more accurate prediction.
Yeah, like in current time.
Oh,
We do talk, like we do study galaxies in the past, and then we talk in that reference.
great. Thank you.
All right. So I just want to make one last announcement, which is that our next condensed matters talk will be done by Al here on October 13th in the same room. So please come and join us again in October 13th.
And you will get extra credit for that day also.
Please thank our speaking video.
Thank you. Thank you.